Next, we're going to talk about covariance and correlation. So let's say I have two different attributes of something and I want to see if they're actually related to each other or not. This will give you the mathematical tools you need to do so, and we'll dive into some examples and actually figure out covariance and correlation using Python. Next, let's talk about covariance and correlation. These are ways of measuring whether two different attributes are related to each other in a set of data, which can be a very useful thing to find out. So let's talk about covariance. So imagine we have a scatter plot here, and maybe each one of these data points represents a person that we measured, and we're plotting maybe their age on one axis versus their income on another. So each one of these dots would represent a person, where say their X value represented their age and their Y represented their income, okay? I'm totally making this up. This is fake data. Now, if I had a scatter plot that looked like this, you see that these values tend to lie all over the place. And this would tell you that there's no real correlation between age and income based on this data, right? Like that doesn't seem to matter. For any given age, there can be a huge range of incomes. And they tend to be clustered around the middle, but we're not really seeing a very clear relationship between these two different attributes of age and income. Now, in contrast, over here on the right, you can see there's a very clear linear relationship between age and income. So covariance and correlation gives us a means of measuring just how tight these things are correlated. So, I would expect a very low correlation or covariance for this data on the left, but a very high covariance and correlation for the data on the right. So that's the concept of covariance and correlation. It measures how much these two attributes that I'm measuring seem to depend on each other. So measuring covariance mathematically, it's a little bit hard, but I'll try to explain it. It's really more important that you understand how to use it and what it means, but to actually derive it, if you were to think of these attributes of the data as high-dimensional vectors, what we're going to do on each attribute for each data point is compute the variance from the mean at each point. So now I have these high-dimensional vectors where each data point, each person, if you will, corresponds to a different dimension. And I have one vector in this high-dimensional space that represents all the variances from the mean for, say, age, for one attribute, and then I have another vector that represents all the variances from the mean for some other attribute, like income. And what I do then is I take these vectors that measure the variances from the mean for each attribute, and I take what's called the dot product between the two. And mathematically, that's a way of measuring the angle between these high-dimensional vectors. So if they end up being very close to each other, that tells me that these variances are pretty much moving in lockstep with each other across these different attributes. And if I take that final dot product and divide by the sample size, that's how I end up with the covariance amount. Now, you're never going to have to actually compute this yourself the hard way. We'll see how to do this in Python. But conceptually, that's how it works. Now, the problem with covariance is that it can be hard to interpret. So if I have a covariance that's close to 0, well, I know that's telling me there's not much correlation between these variables at all. But a large covariance implies there is a relationship. But how large is large? Depending on the units that I'm using, there might be very different ways of interpreting that data. So that's a problem that correlation solves. It normalizes everything by the standard deviation of each attribute. And by doing so, I can say very clearly a correlation of -1 means that there's a perfect inverse correlation. So as one value increases, the other decreases, and vice versa. A correlation of 0 means there's no correlation at all between these two sets of attributes. And a correlation of 1 would imply a perfect correlation, where these two attributes are moving in exactly the same way as you look at different data points. So, remember, correlation does not imply causation. Just because you find a very high correlation value does not mean that one of these attributes causes the other. It just means there's a relationship between the two, and that relationship could be caused by something completely different. The only way to really determine causation is through a controlled experiment, which we'll talk about more later. But let's get our hands dirty in computing correlation and causation and see how we actually do this in Python. All right, let's get our hands dirty with covariance and correlation here with some actual Python code. So again, as I explained in the slides, you can think conceptually of covariance as sort of taking these multi-dimensional vectors of variances from the mean for each attribute and computing the angle between them as a measure of the covariance. And the math for doing that is a lot simpler than it sounds. We're talking about high-dimensional vectors. I mean, it sounds like, Stephen Hawking stuff, but really, from a mathematical standpoint, it's pretty straightforward. So I'm going to do this the hard way. NumPy does have a method to just compute the covariance for you, and we'll talk about that later. But for now, I want to show that you can actually do this, from first principles. So covariance, again, is defined as the dot product, which is a measure of the angle between two vectors, of a vector of the deviations from the mean for a given set of data, and the deviations from the mean for another given set of data for the same data points. And then we divide that by n-1 in this case because we're actually dealing with a sample. So DE mean, or deviation from the mean function, is taking in a set of data x, actually a list, and it's computing the mean of that set of data. And here's a little bit of Python trickery for you. The syntax is saying I'm going to create a new list and go through every element in x, call it xi, and then return the difference between xi and the mean, xmean, for that entire data set. So this function returns a new list of data that represents the deviations from the mean for each data point. So my covariance function will do that for both sets of data coming in, divide it by the number of data points, -1. Remember that thing about sample versus population? Well, that's coming into play here. And then we can just use those functions and see what happens. So in this example, I'm going to fabricate some data that is going to try to find a relationship between page speeds, that is how quickly a page renders on a website, and how much people spend. So for example, at Amazon, we were very concerned about the relationship between how quickly pages render and how much money people spend after that experience. We wanted to know, is there an actual relationship between how fast the website is and how much money people actually spend on the website? So this is one way you might go about figuring that out. So let's just generate some normally distributed random data for both page speeds and purchase amounts. And since it's random, there's not going to be a real correlation between them. So just as a sanity check here, we'll start off by scatter plotting this stuff, and you'll see that it tends to cluster around the middle because of the normal distribution on each attribute. But there's no real relationship between the two. For any given page speed, there's a wide variety of amounts spent, and for any given amount spent, there's a wide variety of page speeds. So no real correlation there, except for ones that are coming out through randomness or through the nature of the normal distribution. And sure enough, if we compute the covariance in these two sets of attributes, we end up with a very small value, -0.07. So that's a very small covariance value, close to 0. That implies there's no real relationship between these two things. Now, let's make life a little bit more interesting. Let's actually make the purchase amount a real function of page speed. So we are keeping things a little bit random here, but we are creating a real relationship between these two sets of values. So for a given user, there is a real relationship between the page speeds they encounter and the amount that they spend. And if we plot that out, we can see that there's actually this little curve here where things tend to be tightly aligned. Things get a little bit wonky down here near the bottom here just because of how random things work out. But if we compute the covariance here, we end up with a much larger value, -8. And it's the magnitude of that number that matters. The sign, positive or negative, just implies a positive or negative correlation. But that value of 8 says, hey, that's a much higher value than 0, so there's something going on there. But again, it's hard to interpret what 8 actually means, so that's where the correlation comes in, where we normalize everything by the standard deviations. So again, doing that from first principles, we can take the correlation between two sets of attributes, compute the standard deviation of each, compute the covariance of each, the covariance between these two things, and divide by the standard deviations of each data set. And that gives us the correlation value, which is normalized to -1 to 1. And we end up with a value of -0.4, which tells us there is some correlation between these two things in the negative direction. It's not perfect. It's not a perfect line. That would be -1. But there's something interesting going on there. And again, a -1 correlation coefficient means perfect negative correlation. 0 means no correlation, and 1 means perfect positive correlation. Now NumPy can actually compute correlation for you using the corecoef function. So if we wanted to do this the easy way, we could just say numpy.corecoef, page speeds purchase amount. And what that gives you back is an array that gives you the correlation between every possible combination of the sets of data that you pass in. So the way to read this is the 1 implies there is a perfect correlation between comparing page speeds to itself and purchase amount to itself, which is expected. But when you start comparing page speed to purchase amount or purchase amount to page speed, you end up with this -0.4005 value, which is roughly what we got when we did it the hard way. There's going to be little precision errors, but that's not really important. Now, we could force a perfect correlation by fabricating a totally linear relationship, and that's what we did in this example. And again, here, we would expect the correlation to come out to -1 for a perfect negative correlation. And in fact, that's what we end up with. All right, so again, a reminder, correlation does not imply causality. Just because people might spend more if they have faster page speeds, maybe that just means that they can afford a better internet connection. Maybe that doesn't mean that there's actually a causation between how fast your pages render and how much people spend. But it tells you there's an interesting relationship that's worth investigating more. So you cannot say anything about causality without running an experiment, but correlation can tell you what experiments you might want to run. So get your hands dirty, roll up your sleeves. I want you to use the numpy.cov function. That's actually a way to get NumPy to compute covariance for you. We saw how to compute correlation using the core coef function, so go back and rerun these examples just using the numpy.cov function and see if you get the same results or not. Okay, you should. They should be pretty darn close. So instead of doing it the hard way with the covariance function that I wrote from scratch, just use NumPy and see if you can get the same results. Again, it's just the point of this exercise is to get you familiar with using NumPy and applying it to actual data. So have at it. See where you get. So there you have it, covariance and correlation, both in theory and in practice. A very useful technique to have, so definitely remember that lecture. Let's move on.